this lecture we are going to talk about certain downstream operations which are carried out at the very end, operations like drying, lyophilization and stabilization. So, here if we want to remove whatever moisture that is present in the product is assumed to be solid. So, either drying, which may involve slightly higher temperature, lyophilization involves a low temperature, and then finally we add stabilizers to prevent the product from degrading. It could be antioxidants or antiozonants or some other enzymes which prevents hydrolysis or reduction and so on actually. So, that is what we are going to talk about today. So, drying, what is drying? This is generally the last step, and we are using a higher temperature, sometimes with vacuum and without vacuum, to remove whatever moisture that is present. So, we need to do that because we want to remove whatever liquid that is present, okay, because if your product is in the liquid form, it may degrade because of oxidation or deamidation. So, we do not want that to happen. It is convenient because pharmaceutical products, drugs may be in tablet form. It reduces the volume because storage, you are using less volume or less space if it is in a solid form rather than in the liquid form. It may be necessary to remove undesirable volatile substances. It is more economical because you may like to store them in dry rather than frozen condition. You can prevent microorganism growth because there is no moisture, so the bacteria might not grow. If there are any expensive organic solvents, then by doing a drying you may be removing those organic solvents or recovering those organic solvents. The types of dryers, you have vacuum shelf dryer, that is oven with trays. So, this is generally a batch type of operation. Rotary vacuum dryer, this could be a continuous operation. Freeze dryers, this is almost like lyophilization, and then spray dryers. So, it uses atomization and vacuum and so on actually. So, we will look at each one of them little bit in more detail later. So, hot air dryers, so you have hot air flowing, and then maybe there are trays on which the solid is kept which gets dried. So, a moving stream of hot air in contact with the product. So, it is generally by convection, like kiln dryers, cabinet dryers, tray dryers, compartment dryers, tunnel dryers, conveyor dryers, bin dryers, fluidized bed dryers, pneumatic dryers, rotary dryers and spray dryers and so on actually. So, a lot of different types of dryers, and all of them are based on hot air flowing in. Vacuum shelf dryer, they are also called tray dryers. It consists of a cubical chamber, heated support shelves inside the chamber. There is a vacuum source, there is a condenser for collecting the solvent or water. It is widely used in pharmaceutical, temperature sensitive or easily oxidizable material, and we can do it in small batches for high cost products. So, this is a tray dryer. So, you have lots of trays, you have your product which is collected, initially the wet product, and then hot air flows upwards. So, the air flows through these beds and thereby it is drying the material. So, it is by convection. So, once it is done, you stop the drying process, cool it down, take the solids out, again charge with the again wet solids and so on. So, generally it is carried out in batch mode. So, direct contact drying, you may have the material which is hot. So, your solid which needs to be dried is dumped on this, and it is more of a conduction based heating. So, it gets dried because of this conduction actually. Like drum dryers, roller dryers, vacuum band dryers, you may even have belt dryers. So, the belt itself may be very hot, where the drum itself may be very hot, and the solids, the wet solids, when it comes in contact, so the moisture is removed. So, that is based on conduction approach. So, 100 degrees is used. One problem is the heat sensitive material like food material may get damaged. So, we can carry it out under reduced pressure and lower surface temperature, so that if it is temperature sensitive material, it does not get damaged. Rotary vacuum dryers. So, wet feed is charged as a batch, and it is subjected to indirect heating, and there could be agitation also. This could be carried out in vacuum. Okay. So, that is called rotary vacuum dryers. Okay. So, we can even recover the solvents, especially in this type of dryers, whereas in the other type it may be more difficult to recover this freeze dryers. This is done at low temperature. This is almost like lyophilization. We will talk about it more detail. So, removal of water from a specimen after it has been frozen. So, it is very good for heat labile materials including proteins, antibiotics, vitamins, blood plasma, hormones, tissue, microorganisms, so on actually. Then you have the spray dryers like your coffee powder or instant milk powder and so on. So, you can get a dry powder from a liquid or a slurry. Okay. This is very good for thermally sensitive material. So, you do not have to heat much, but you apply very high vacuum and air is heated and it flows and carries away the moisture. Sometimes you can use even nitrogen, hot nitrogen if the material is oxygen sensitive or if it is flammable solvent is there. So, where do you use them? You use in food industry, pharmaceutical industry, even industrial like paint, pigments, ceramic. So, lot of applications nowadays the spray dryer has come into quite a lot. Typically it looks like this, there is a long tall chamber. So, you have the slurry feed and it is atomized and it comes out as fine droplets, there is hot air coming in. So, it carries the moisture, okay, as it comes down. Because it is fine particles, you end up with solid particles which are corrected. So, the solid particles we are talking in terms of microns. So, we could get very fine micron particle using this type of technique. So, if the feed is atomized to 100 micron, then the droplet, then you have 15,400 feet square per pound of surface area. If the feed is optimized to 20 microns, then we are talking about 77,000 feet square per pound of surface area. Okay, so, the surface area is like almost d square. Okay, so, finer the surface area where then finer the surface area, that means diameter becomes smaller and smaller. So, the surface area becomes larger and larger actually. That is the advantage of this type of drying. So, what are the important parameters in a spray dryer? Evaporation rate, particle size, distribution of the product. So, evaporation rate determines the amount of air needed. If I want to evaporate at certain rate, that means I am evaporating the solvent or the moisture. So, it tells you how much air I will require for drying. So, that will determine the cost of the air handling system, either a compressor or a blower. The particle size distribution, that affects the choice of how to do the atomization. So, that will tell you what will be the size of the spray drying unit. So, the former will tell you the size of your air handling system, the latter will tell you the size of your spray drying chamber. For a given evaporation rate, higher the delta T, you will require less process air. So, if you require less process air, you will have a smaller and less costly spray drying system. But of course, if you are talking about high delta T, you have to be very careful your material does not degrade. Okay. So, but if it cannot withstand very high temperature, then your delta T has to come down. So, if it is material can withstand, then we can have higher delta T. So, the system will be quite small. Very short drying time, that will give you a very low product temperature. So, your product will not get degraded. Droplets of the spray usually have diameter in this range 10 to 200 micron. So, it gives you a very large surface area. Okay. So, it is used as I said quite a lot in food industry, milk processing, milk products and so on, pharmaceutical products and so on actually. So, non-hygroscopic materials can be dried to almost 0 level, because most of the biological products are hygroscopic. So, it will have some residual moisture content depending upon the relative humidity. Hygroscopic materials, you will have bound moisture and unbound moisture. So, bound moisture is within the capillaries, whereas the unbound moisture is generally present in the material as surface tension. Okay. So, then we have the equilibrium moisture content, that is the moisture content which the material will hold at a given relative humidity. So, at a given relative humidity, we cannot bring the amount of moisture below that equilibrium moisture content. Okay. So, if you look at the graph between moisture content on the x axis and the relative humidity on the y axis. Okay. So, as the moisture content increases, as the relative humidity increases. Okay. This is called the equilibrium moisture. So, we have the bound moisture here and we have the unbound moisture here. Okay. We have the bound moisture, unbound moisture here, and this is the equilibrium moisture, and whereas this is the free moisture. So, we can remove all the free moisture, but as soon as you reach the equilibrium moisture content at a given relative humidity, you cannot go below that moisture content. Okay. So, when you are drying material, initially the moisture is so much that at a constant rate the moisture is removed, that is called the constant rate drying. Once the moisture amount goes down, moisture is present only inside the capillaries. So, the water has to come up to the surface, and then it has to get evaporated. So, the drying rate goes down. So, here the controlling factor is how the water diffuses out from the capillary to the outside. Initially you have plenty of water on the surface, so water is evaporating fast, that is why you have constant drying rate. But once that has depleted, water that is present inside the solid inside the capillaries has to come out or diffuse out to the surface and then dry, and that is called the falling rate. Okay. And finally, you reach the equilibrium moisture content. Okay. Beyond that you cannot dry the material further. Okay. This is how it looks like. Whereas, if you look at the rate of drying, you have the constant drying period and then the falling drying period, and then this is the equilibrium moisture content. Okay. This is the constant drying where the rate of drying is constant. So, the concentration where there is a shift from constant to falling rate, that is called critical moisture content. So, equilibrium moisture content is the final value which you can reach for a given relative humidity, whereas critical moisture content is the connecting between the constant rate period and the falling rate period. So, generally there is an equation like this. Okay. So, you have the amount of rate of moisture removal as function of A, and R is the constant rate drying. Okay. So, and then you have two terms here, one relates to the constant rate and one relates to the falling rate. So, this one is falling rate, this one is constant rate, and then we come to a term called the critical moisture content. Okay. So, until critical moisture content, it will be the constant rate period, and after that it will be falling rate period until it reaches the equilibrium moisture content. Okay. This is a typical equation, simple equation which relates all these parameters. So, heat transfer can happen because of conduction, and you all know this equation, you must have studied long time back. Rate of heat transfer is equal to K, thermal conductivity, area A, T1 minus T2. Okay. This is the driving force divided by the L is the length. So, T1 minus T2 is the driving force, that is in the conduction. If you take convection, heat Q, amount of heat you need to supply U A delta T, A is the area, U is the heat transfer coefficient, overall heat transfer coefficient, delta T is the driving force. Okay. U depends on the physical properties of the solid and the air flow rate and so on actually. Okay. So, U is related to individual heat transfer coefficients. Okay. Heat transfer coefficients related to the hot fluid side, heat transfer related to the cold fluid side, and the thermal conductivity of the material. Again, you might have read this equation long time back. So, this relates the overall heat transfer coefficient with the individual heat transfer coefficient. So, if the wall thickness of a tube is small, then all the areas will be equal. Okay. So, we have a equation of this form actually, simple equation of this form. We have continuous sterilizers where you have rapid heating and cooling taking place. Okay. You quickly heat and then you quickly cool, generally it is used for pasteurizing milk. As you know, milk you do not want to heat and keep it for a very long time because it may get denatured. So, this type of rapid cooling and rapid heating and rapid cooling is done to kill the bacteria, at the same time not lose the flavor of the milk. So, if you go to the heating because of radiation, then you must be knowing this heat transfer is equal to sigma A T power 4, A is the area and T is the temperature, absolute temperature. Okay. And sigma is a constant. So, we looked at drying. Now, let us look at lyophilization. This is very common in biological systems because most of the biological products biomolecules are temperature sensitive. You do not want to heat it up and make lose its activity. So, generally lyophilization is resorted to so that you handle at low temperature. So, it is freeze drying, removal of water from frozen material. It is very good for preserving microbes and heat sensitive materials such as proteins, plasma and so on. So, this requires both the temperature and pressure to be controlled during the process. Okay. It can dry a liquid product contained in vials also, it can dry products into solids and so on actually. So, if you look at the phase diagram for water, what is a phase diagram? You have the temperature, you have the pressure and you have solid, liquid, vapor, okay, solid at lower temperature, okay, vapor at higher temperature and lower pressure, liquid at higher pressure and higher temperature. Okay. At one point here, this is called a critical point, we have this supercritical fluid here, okay, then we have the compressed liquid. There is another point which is called the triple point where the solid, liquid and the vapor are in equilibrium. Okay. This is called the triple point, solid, liquid and vapor are in equilibrium. This is where you operate. For example, for water, if you look at it's minus it's 0.01 centigrade and 4.6 mmHg. So, I can move from liquid to vapor and then I can move to solid and then I can move to liquid, or I can move from solid to vapor without going into liquid at this triple point. Otherwise, normally if you are here, for example, you have to go from solid to liquid and then you come to vapor. Okay. If you are heating ice, you will go to water, then you will go to vapor. But if you are here, you can directly from solid you can go into vapor. Okay. That is the beauty of it. So, that is what the lyophilizer makes use of, that is the principle of it. So, this is the triple point 0.01 C centigrade and 4.6 mm. Okay. So, we can directly move from solid to vapor. Okay. So, if I am having liquid water, I can move from liquid to solid, okay, make it into ice, and then I do not want to go again to liquid, I want to go into vapor. So, what I will do? I will reduce the pressure and then I will increase the temperature. So, it will go from solid to vapor. So, I am here. So, from here I go like this and like this. So, liquid is converted into vapor at low temperature. Remember that is the beauty of lyophilizer. Okay. So, cooling of the product to a sufficiently low temperature to solidify, reduce the pressure in the chamber to below the vapor pressure of the triple point, okay, and then increase the temperature so that it passes directly from solid to the vapor. That is what it is, right. So, unbound water is removed in a drying phase called primary drying, and then higher shelf temperature and addition time are required to move the bound water in the secondary drying. So, you have a primary drying, unbound water, secondary drying where the bound water is removed. Okay. Generally it takes a long time, almost 48 hours for performing lyophilization. So, we can do lyophilization of lot of products using this type of techniques actually. So, freezing, primary drying, secondary drying. So, approximately 90% of the water is removed in the primary drying, that is by sublimation, and then secondary drying where you have the bound water, you can bring down the moisture content to less than 1% here, okay, using this secondary drying. So, bound water is removed by desorption resulting in a product that has a very low amount of moisture. So, in the secondary drying the moisture content is reduced very less to almost 1%. Then removal of water from the shell is a surface phenomena actually. So, you also use 30 to 40 degrees for 4 hours to remove all the whatever moisture is there from the product. Okay. Larger the surface area of the frozen material, faster will be the rate of lyophilization. Thicker the frozen material, slower will be the rate of lyophilization. These are very logic, right. So, you want to spread out the material to a very large surface area so that lyophilization is very good. Okay. So, what are the advantages, disadvantages? Advantages of lyophilization: preservation of chemical and biological potency in the final product, protection from solution effects and chemical degradation, speed and completeness of rehydration compared with dry powder. Okay, it can be quickly again rehydrated by following lyophilization. So, typical setup. So, what you have here, you have a frozen solid to be dried, okay. Then in the below the triple point it becomes vapor, and then it is condensed as ice here, and then which is ice is drained. So, you are applying a vacuum here. Okay. This is how set up. So, it is generally a batch process. What are the disadvantages? High capital cost of the equipment, it is 3 times more than a dryer, that is much cheaper dryer. High energy cost because you use lot of cooling and vacuum, long processing time, we are talking almost 48 hours. But for majority of high value proteins, peptides, there is no other way except resorting to lyophilization. Let us look at stabilization. You want to stabilize your product if you have say enzyme or a protein, so that you can increase the shelf life, you do not want it to degrade because of say hydrolysis or oxidation or amidation. So, to prevent degradation, could be thermal, chemical, biochemical, increase shelf life, prevent formation of toxic metabolites, maintain customer appeal, all these, that is why you do this type of stabilization. So, what do you do? How to stabilize? We can remove moisture by drying lyophilization, that is a very good stabilization. Even spray drying, add a stabilizing agent, add antioxidants which are radical scavengers, it will not allow oxidation to take place. Okay. If there are any radicals or if there are any oxidant formed, it scavenges, store at low temperature, prevent bacterial fungal contamination, stabilize the 3D structure of protein, immobilization of enzymes, that also improves the stability of the enzymes. So, what are the different techniques for immobilizing enzymes? We can do entrapment, covalent binding, cross linking, adsorption. Let me show it in the next slide. So, we can entrap our enzyme on through a protective layer of polymer. So, the enzyme is inside, so there is a layer of polymer, so the enzyme does not denature. Another approach is covalent binding. So, the enzyme and the support are covalently connected here. So, the enzyme is covalently bound to the support, so the enzymes retains its activity. Cross link, the enzymes can be cross linked, okay, to each other, so that they do not lose their activity. Another approach is using enzyme with the support, okay. So, that is the enzyme is adsorbed on the support. So, mostly it is non bonded interaction, unlike the covalent immobilization where there is a bonded interaction between the support and the enzyme. Here it is more non bonded type of interaction. All these will prevent the stability and the activity of the enzyme. Of course, the enzyme may lose little activity, but generally they are kept for a very long time. Especially immobilized enzymes are very active, much longer than native enzyme, and if you are doing any reactions, we can do it for many cycles without any problem. Biocatalysts can be entrapped in natural polymers like agar, agarose, gelatin, alginate, carrageenan. So, we can use all these type of biopolymers. Okay. Number of synthetic polymers also we can use, like polyurethane, acrylic polymers, acrylamide. Okay. Glutaraldehyde has also been used for cross linking enzymes in support. So, different approaches can be adopted for immobilizing these enzymes onto support. Okay. So, what are the forces? You have hydrogen bond, hydrophobic interaction, electrostatic, van der Waals forces, disulfide forces, salt bridges, all these are various forces by which stabilization of the protein can be achieved. So, for proteinaceous preparation, inactivation, why do they get inactivated? It could be addition. So, we can retard these inactivation by adding chemical additives like glycerol, cooling, low temperature, chemical modification like immobilization, sequence alteration, that is protein engineering, freeze thaw, lyophilization, addition of water soluble glasses. So, all these are different techniques by which we can slow down. A range of substances can addify to be purified therapeutic protein in order to stabilize, such as stabilizing protein in different ways. Serum albumin, it can stabilize polypeptides. So, there are different other approaches by which we can stabilize them. For example, HSA, human serum albumin, is used to stabilize some biopharmaceutical parental administration to human. It is used in combination with additional stabilizers such as amino acids and carbohydrates. Serum albumin itself is a stable molecule, it can withstand low pH or even elevated temperature. So, when we use this, it decreases the level of surface absorption of active pharmaceuticals to the internal surface of the final product container. Okay. So, that is the advantage of using HSA, human serum albumin. Okay. So, that is a good stabilizer because it can take up very low pH as well as slightly higher temperature. HSA is now discouraged due to accidental transmission of blood borne pathogens. So, there are now recombinant HSAs, human serum albumins are coming into, and glycine also stabilizes the interferon preparation as well as EPO, ethyl protein. Okay, amino acids are also added to final products at a concentration that also can act as a stabilizer. Okay. So, these amino acids can reduce absorption of the product, inhibits aggregate formation, and it directly stabilizes the conformation of some proteins against heat denaturation. Okay. Polyols, and these are molecules displaying multiple hydroxyl groups, that is why they are called polyols. So, they are very good for polypeptide stabilizing agent. So, the polyols can stabilize proteins in solution directly, carbohydrates added to pharmaceuticals prior to freeze drying to provide physical bulk to the freeze dried cake. So, polyols can also act as a very good stabilizing agent. Polyalcohols include sugars, sugar alcohols, etc. They modify the water environment surrounding the protein, competing for replacing the free water. So, they modify the hydration shell of the protein. Basically, they also compete with the water that is present in the protein. So, they modify that way they stabilize the protein. You can even stabilize with polyelectrolytes, that is polymers of varying sizes and charge. Okay, they can also act as a stabilizing agent. Okay. So, they interact with the protein through electrostatic forces, and so they stabilize the protein. There are surfactants which are well known for protein denaturants. When they are sufficiently dilute, when they are very dilute, they also exert a stabilizing influence like polysorbate. Proteins display a tendency to aggregate at interfaces, especially air liquid or liquid liquid, and this is also promoting denaturation. But if I add surfactant, what happens is the surfactant reduces the surface tension of the solution and increases the solubility of the protein. So, this protein will not come to the air water interface or air liquid interface, okay, or liquid liquid interface, thereby protein remains in the solution, and so it does not get denatured at all, or it does not allow the protein to aggregate. So, there are many excipients added to protein, especially in biopharmaceutical industries, which stabilize like serum albumin, various amino acids, various carbohydrates, alcohols, polyols, surfactants. So, all these help especially when they are added as a during the finished product to stabilize a biopharmaceutical products. Human serum albumin is also added as a stabilizer, as you can see for large number of interferon gamma, interferon alpha and beta and so on. HSA acts as a very good stabilizer. Okay. Amino acids, carbohydrates and polyols, amino acids like glycine, alanine, lysine, threonine, carbohydrates like glucose, sucrose, trehalose, maltose, polyols like glycerol, mannitol, sorbitol, PEG, all these are very good stabilizers that are used in biopharmaceutical industries, and they are also biocompatible. So, they enhance the shelf life of the biopharmaceutical product and also prevent the protein aggregation. So, today we talked about a mixture of downstream activities. Okay. Generally these downstream activities are resorted to at the end of the operation, that means at the end of the product purified product, either I want to make the product into a solid and then dry it using temperature, I want to either or lyophilize it at low temperature, so that I end up with a solid product. So, prior to that I may like to add a stabilizer, because I do not want my product to lose its activity, a protein or an enzyme. So, I add different types of stabilizers. So, I talked about different types of stabilizers. If you have enzymes, you can immobilize the enzyme, thereby increasing the shelf life of your enzyme. Thank you very much.